All right, now we're cooking. Go ahead and share. Something stupid happens. All right. I only got 11 folks. Well, there's no waiting room, so I'm gonna go ahead and jump in. All right. So we left off on Monday talking about macro versus micro investigation, or the way we study chemistry on the macro level, the micro level, and the symbolic level. Somebody tell me what the difference is between macro and micro.
Macro, you can see with the naked eye, and micro you can't.
Good, good, excellent. So on a macro level, everything is tangible and visible. So we gave the example about like the iceberg that had clouds over it and it was floating in a lake. So the water was liquid, the iceberg was solid, and the clouds were gas, right? And we talked about how we could see that, but what made each one a liquid, a solid, or a gas, we couldn't see, which was the arrangement of the water molecules, all right? So for something that's on the macro level, it's visible to the naked eye, it's tangible, you can measure it on a scale that's visible to the naked eye. And then for something that's micro, it's the opposite. It's invisible to the naked eye. The scale is much smaller. And then you have to use specific types of instruments to measure things on the micro level. And then to take that even further, because we're going to talk about physical properties, maybe not today, but definitely Wednesday, because I think Friday, because I think we're out Monday. Macro properties are like volume, pressure, temperature, density, and then micro properties are like bonding and molecular structure, the electron configuration. Those are all micro properties, things that you can't see with the naked eye. So today we're going to shift gears and we're going to start talking about classes of matter, right? So how to classify matter. So today is the 12th, and we're going to talk about classification of matter. All right, and before we do this, again, if you've had chemistry or physics on a high school level, you know the answer to this. Some of this is redundant, but again, we are laying a foundation for everything that we're going to be doing going forward. So it's good to deal with the redundancy for now, and make sure that we know we have a good foundation to work from. All right. So let me ask somebody, can somebody tell me what the 4 phases of matter are?
Is it solid, liquid,
Okay.
gas, and plasma?
Excellent. You're exactly right. So solid, liquid, gas, and plasma. All right. So for these are, let me move this down because I need to put a at least put a header up here. That's the beauty of the iPad. So 4 phases of matter: solid, liquid, gas, plasma. So when we talk about a solid, let's take this back to what we were talking about the other day with the iceberg and the water and the clouds. What do we know about what a solid is? We know that if something is a solid, it has a shape, a definite shape. Right, it can be altered physically, but for the most part, it has its own shape. What do we know about how the atoms or the molecules that make up a solid, what do we know about their arrangement based on what we looked at yesterday? And I'll even pull that picture back up just to kind of help you think about that. What do we know? It's the middle picture. That's the picture of the solid, how the water molecules are actually arranged in the solid ice.
Yesterday,
I'm sorry, Monday, my bad.
oh, Monday, we talked about how solids are closer together and they barely move.
Excellent, excellent. So solids have a well-ordered arrangement of atoms or molecules. So let's add that to the definition. So a well-ordered atomic or molecular, because some solids are indeed made of molecules. So solids have a definite shape, and they have a, well, I misspelled order, sorry about that. And a well-ordered atomic or molecular arrangement. So we know that about solids, especially based on what we already saw, right? Liquids are a little bit different, right? A liquid is, if matter is in liquid form, it takes the shape of wherever you put it. If you put it in a circular container, it's going to take the shape of that container. If you put it in a cylindrical container, it's going to take the shape of that. So we know that liquids take the shape of their container. What do we know about their arrangement? If a liquid is made up of specific types of molecules or atoms, what do we know about their arrangement? Is it as ordered as a solid, or is it less ordered?
Less order.
Less ordered, much less ordered, right? Good. So much less ordered atomic or molecular arrangement. That's why liquids have the properties they have, excuse me, because of the way the molecules are arranged. All right. And one element in particular, because again, this can be on an atomic level where it's just one element that's made up of multiple atoms of whatever, sodium, chlorine, whatever. For mercury is a metal, and most metals are solids, but mercury is a liquid at room temperature. And I'm not sure if you've ever broken a mercury thermometer. Hopefully you haven't, but if you have, mercury is a liquid, and when mercury is released from whatever container it's in, it's also a poison, and also causes brain damage. But whenever it's released, it's very difficult to contain. It's a very non-viscous liquid, and if you lose it, it's everywhere. Very difficult to clean up as well. And I say that having cleaned up mercury spills, teaching organic lab where students have broken thermometers. That's why most of the time when we have freshman lab, the thermometers have that red liquid in them instead of mercury, and that's just alcohol. So if you break that, no problem. But if you break a mercury thermometer, you got a lot of, it takes a lot to clean that up. All right, so let's talk about gases. All right, the thing about a gas is that it is also going to assume the shape of its container, but also the volume. So it's going to assume the shape and the volume of its container. what do we know about gases as far as the distance between the atoms or molecules that make them up?
Spaced out.
They're spread out.
Yeah, very, very, let me fix this, sorry about that. It's very spread out, right? It's not trying to do that. Right, if the atoms or the molecules are very spread out. So we're gonna say it has a loose atomic/molecular arrangement, and those molecules that make that gas up they have a large distance between them. So the distance between them, we're going to call intermolecular. What else the other thing we know about these gases is that those particles that make up the gas, whether it be in a single element or a compound that's a gas, is that they're moving very rapidly as opposed to a liquid or a solid. Gases are also pressure dependent. All right. So the final state of matter that exists is what we call plasma. And this is not blood plasma. It's actually a gas, but the gas has some specific qualities about it that make it plasma. Whoever gave me, I didn't see who it was that answered the question about the 4 phases of matter, but can you tell me what plasma actually is?
Isn't plasma like gas, but I think superheated past the point of it?
Okay, so it is hot. It's very hot. You can find like plasma in stars. Plasma is the sun has some of its composition is plasma. So it can be superheated, but it's also there's another element to it, or another component to that definition, and that is charged. And it's the charge that helps give it its physical qualities. So plasma is a charged gas, right? You might see it referred to as an ionized gas. So it's made up not necessarily of a single element or a singular atoms, but it's made up of what we call ions. This is a very important term, ions, because what an ion is, it's a charged particle. And ions can be positive or they can be negative. And we haven't learned about ions just yet. That's coming up when we start studying the periodic table, but this is a great place I like to introduce information when it comes up, because then it gives you another teaching tool. You don't have to just wait, and then, oh, we'll learn that later. If we hit it, we're gonna learn it now. So they can be positive, and we call those positive ions cations, or they can be negative. And we call negative ions anions. Very important, especially when we start naming compounds and we start putting compounds together. Every compound is that's not organic, right? That's not covalently bonded. It's going to have some ionic component to it. Like for example, if I take, and this is not plasma, but we're just talking about ions right now. If I take sodium, which has a positive charge, and chlorine, which has a negative charge. When those two come together, they are attracted to each other because of that, because of the difference in the charges. So this is a cation, and then over here, chlorine is an anion, right? And meaning that's how you know it's negative, and cat meaning positive. So that's how you know it's positive. All right, so plasma is a ionized gas, meaning that it's a gas that's made up of charged particles that are either positive or negative. And I'm not sure, I mentioned this to the morning class. I'm not sure how many of you are old enough to remember, or you may even have one, when plasma TVs first came out, right? I know I bought one when they first came out. It was $3,500, and I should have waited, because after the plasma, then you had the LCD televisions, then LED televisions, and so now the plasmas are outdated. I still have my plasma though. It's a 50-inch, I think, a 45-inch, 50-inch, something like that. Paid $3,500 for it. I have a 65-inch LED in my living room that I paid $500 for. So as the technology progressed and got better, it also got cheaper. And that's, to me, that's why I never jump anymore at tech innovations. You know, the first, you know, if you want the first generation of whatever, you can guarantee that it'll be obsolete in a couple of years, because people are going to innovate and, you know, do other things with that. But anyway, having said that, now we're going to move on to the properties of matter, because we know what the four, let me zoom that so you can see it. We know what the four phases are: solid, liquid, gas, plasma. So now let's talk about the properties of matter, right? So matter is going to have, again, when we talk about matter, we say that it's anything that that has what and takes up what?
Mass and takes up space.
Excellent. Any matter is anything that has mass and takes up space. Good. So let's talk about the properties of matter. So let's going to move. This is another subtopic. Fix that E. I promise you. I wish I could write with a stylus, but it just doesn't click. So you have to, if my handwriting is bad, just it used to be worse. So so I'm thankful that it's not as bad as it was. So the properties of matter, one of the things that we know about matter, we said that it has mass. Right? And mass is very simple. It's a measure of the amount of matter in an object. And I know these are a lot of definitions, but just stick with it. That means the first test is going to be very easy. A lot of definitions, few calculations. All right, so we're going to stick with it, because as we learn these definitions and these concepts, they will apply to other things that we do going forward. So don't lunch on this part, because when you see this stuff again and have to apply it, you want to have a good handle of it, right? And a good understanding of it. So a measure of the amount of matter in an object. Right, so everything has mass, even if it's an electron that orbits the nucleus of an atom. If it's a proton, if it's a neutron, it doesn't matter. Everything has mass, and all matter has mass, no matter how small or how large it is, right? The comparison between different types of matter, that's always going to be different based on size, but the measure of the amount of matter in an object, we call it the mass, right? And you'll notice when we do labs, you'll notice that when we're talking about weighing something out, we always say take the mass. We don't say take the weight, because weight is different. Weight takes gravity into account. right? So weight is the force that gravity exerts on an object. Right? And so when we think about weight, right, the mass is involved in there because it's the force equals mass times acceleration. So if you want to find out what the mass of an object is, then we need to know what the force is that's acting on it, and we need to know the acceleration. In most cases, if we're talking about on Earth, the acceleration is going to be gravity, right? So 9.8 meters per second squared. If you have taken physics in high school, that's a number that's probably familiar to you. All right. So the question is mass or mass and weight the same? And the answer is no. Weight changes, right? Your weight can change based on what type of the gravity in your environment. So if you're on the Earth, your weight may be one thing. If you go to the moon, which has 1/6 the gravity of Earth, then your weight is going to be different. But mass never changes, so, right? So weight changes, but mass doesn't. All right, and that's a constant. So you can change the weight based on the force and the acceleration, but you cannot change the mass. All right, so the weight can change based on what the force is that's acting on the object. All right, so the force or the acceleration can affect the weight. All right, any questions so far? Let me know if I'm going too fast or you missed something or something is not clicking. Please say something and feel free to unmute and ask questions. All right, so as far as matter's properties are concerned, right? Matter has mass, and that mass you can also convert into a weight if you know the force and the acceleration that's acting on that matter. There are other properties of matter, physical properties, that we're going to talk about a little bit later, but right now we just want to introduce that, right? And so now we want to introduce another idea dealing with matter, and that is how to classify it. Right, and again, when we talk about properties of matter, there are macroscopic properties as well as microscopic properties, right? Mass is a macroscopic property because you can take the mass of any object and get a number and get a measurement that's a tangible measurement of what you're seeing, right? One microscopic property of matter that you can't see is, again, like the arrangement of the atoms or molecules that make it up, right? So all these concepts kind of tie together. And so when you start making those connections, it's going to make the understanding of chemistry much easier. So when we talk about classifications of matter, we actually are dealing with two different classifications, right? Matter is either going to exist as a pure substance, right? And that can be a element or compound, which I'm going to explain. Right? Or it can be a mixture. right? Let me go ahead and say up front, for something that is a pure substance, it's either an element or a compound. What we're going to be looking at in that particular case are chemical properties, because compounds are formed chemically. All right. Elements are formed chemically. Mixtures, however, are either homogeneous or heterogeneous. Right, so that's different. Here, you're talking about physical, something that's physical. Right, you physically take two things and put them together. And you can physically separate them. Right, so you can physically add them together, or you can physically separate them. And one I'm going to talk about in a minute, like some examples of that. But let me I'm going to grab this chart, because this chart is going to help us to kind of understand the differences between what we call a pure compound, I'm sorry, a pure substance versus a mixture. All right. So matter itself exists, right? We know that it can exist in 4 phases. The question we ask now is whether or not that matter, can y'all see that? Okay.
Yes, sir.
All right. So we're going to ask this question. Does the matter, let me pick a different color. I know that's too dark. Right? Does it have constant properties and composition? When we talk about the composition of matter, what we're talking about are the atoms and the elements that make that matter up, right? Is it constant all the way through? Like, let's say, for instance, if I take a block of sodium, and sodium is like really explosive, and you have to store it in oil and all this stuff. But if I take a block of sodium and I chop a piece off, and I chop a piece that weighs a milligram off, and then I chop off another piece that weighs a gram, regardless of the mass, regardless of the size, that sodium, the composition of the atoms that make that sodium up is going to be the same no matter what, right? So if the properties and the composition are constant, yes, then we can say that it is a pure substance. All right. And then if the pure substance can be broken down into other substances or other compounds or other, how do I put this? If the components can be taken apart chemically, then we call it a compound. Right? So when it says simplified chemically, that means that I'm taking whatever the components of that substance are, and I can break them down. I can make something new from it, right? So if the answer to that is yes, it's a compound. If the answer is no, then it's an element. So I'm going to give you a couple of examples of that, and then also some examples of mixtures, because if the matter doesn't have a constant properties and composition, then it's a mixture. And then that mixture can either be homogeneous, meaning that is the composition is uniform throughout, right? Then it's homogeneous. If it's not uniform, then it's heterogeneous. So a good example of a homogeneous mixture is, let's say, for instance, Coca-Cola. I don't know how many of you actually drink that. My daughter loves it. All of a sudden, she just became a Coca-Cola fan. But that Coca-Cola is made up of sugar, water, cola, right? The cola bean, all that stuff. But when it's mixed together, right, it's a solution. Right? You can't tell the ingredients apart. You can separate them event, you can separate them physically because a mixture can be physically separated, but you can't tell them apart. Now, an example of a heterogeneous mixture would be like, I used this example earlier. How many of you have ever eaten at Bonefish Grill?
I have.
When they bring out the bread, they also bring this mixture, right, of olive oil and pesto and salt and pepper. To me, that's the highlight of the experience. I love that dipping sauce. But the right, so that dip is composed of olive oil, pesto. It's got a bunch of spices in it, but these are the main ones, and then salt and pepper. And when you look at that dip, it comes in a little small dish. You can see all the ingredients. So if something is heterogeneous, that means that the things that you added together to make that mixture, you can actually see the different parts. And depending on let's say, for instance, we had a mixture of sand and rocks, right? If I take a scoop out of one side of a bucket, there may be 10 rocks in that scoop. Or I take a scoop out of another side, that may be 20. That's what it means by being uniform throughout. If it's non-uniform, then that means it's heterogeneous. If it's uniform, that means it's homogeneous. All right. So now let's talk about these pure substances, because if you talk about an element would be, let me say sodium. I like sodium, right? Sodium is an element, and no matter what I do to that sodium, I can't turn it into something else. No matter what I do to it, I can make it into something else if I react it with something. But the sodium itself, if I chop off a piece, it's not going to become sodium chloride. It is what it is. Every part of that element is sodium atoms. And so I can't break them down any further. But if I think about a compound, in this case, I'm going to say sodium chloride, right? I can react that sodium chloride with something and break those two atoms apart and so take that compound back to its elemental form, right? So let me give you another example, because when we think about the constant composition and constant properties, I want to give you an example of that kind of will make a little bit more sense when you think about like what a compound actually is, right? So what elements are elements. You can do whatever you want to do to them, but the composition is going to stay the same. You could take sodium and smash it. You can chop it up into small pieces. You can pulverize it, whatever. At the end of the day, it's still going to be sodium atoms that make up that element and nothing else. Compounds are a little bit different. So we have a compound. Let me show you. Don't panic because you haven't seen 6-membered rings before. Well, you may have. But this is an example of what we call an organic compound, sucrose. I got to zoom in a little. Don't do that. All right, so this is sucrose. It's a sugar. Well, this is table sugar, actually. Excuse me. And don't worry about trying to duplicate this. It's fine. It's no big deal. All right, so this is OH. This is OH. All right, so sucrose which is just cane sugar, is made up of two pieces, right? You have a glucose part, and then you have a fructose part, or fructose, however you want to pronounce it, right? You can take this compound, you can heat it up and convert it into something else, right? You can break this down by breaking the bonds that are here. These are this bond right here. And every place where you see in the ring that's not indicated to be another atom, those are carbons, right? So you can break that carbon oxygen bond and break this down chemically. That's what that means when to break a compound down chemically. All right. Another thing about this is that the composition, no matter if you take 10 grams of sucrose, 100 grams of sucrose, or 5 grams of sucrose, it doesn't matter. It's always going to be composed of the same thing. It's going to be 42.1%, sorry. Carbon. It's going to be 51.4% oxygen and 6.5% hydrogen. It doesn't matter what you do, where you take it from. It doesn't matter how much you take, right? That's what it means to have a constant composition. If I have a bowl of sugar and I take a spoonful out the middle of the bowl, as opposed to taking a spoonful from the edge of the bowl, it's not going to matter. It's still going to have the exact same composition. Right, so it's always going to have this 42 to 51 to 6 ratio of carbon, oxygen, and hydrogen. So that's what that means when it says that it has a constant properties and constant composition. And if you look at fructose, you can see it's made of two separate molecules. So that means that you can chemically break that apart and break it down into its components. All right. So what we know about this, we know a couple of things. We know that elements combine to make compounds. That's something that we can say very definitively. Right, elements combine to make compounds. And then when you make compounds from elements, and up here you can see for sucrose, the elements that make it up are carbon, oxygen, and hydrogen, right? But when you make compounds from elements, the chemical and the physical properties are going to change. Right, so different chemical properties and physical properties. All right. So elements combine to make compounds. Compounds, when you put those elements together, the compounds that they make are not going to be the same. They're not going to have the same chemical and physical property. And let me go back to an example that we've already looked at. So we take sodium, a block of sodium, right? This is a very soft, silvery solid. It looks kind of great, silver, grayish silver. Very soft metal. You can actually cut it with a spatula in the lab. You can shave off little pieces of it. You have to store it in oil because it's highly explosive when it's exposed to water. I'm sure some of you have probably seen a YouTube video where some chemistry professor just takes a block of sodium and tosses it into a lake. It's highly explosive when you expose it to water. And then if we took that sodium and we put it into a beaker or Erlenmeyer flask, and sealed it up, and we piped in chlorine gas. This is my cartoon depiction of what a gas would look like, right? Chlorine is a greenish yellow gas. Right, and we pipe that in, and we have the sodium there, right? What we're going to get out is a compound known as sodium chloride. Right, so these are the elements that make up the compound sodium chloride. Fix that. Right, so that's different. This is table salt. I'm sure most of you already knew that, but that's where it comes from, combining the elements of sodium and chlorine. Now, the thing is, people don't just make salt. So you can find it, you mine it and purify it, and then you sell it. But you could make it if you chose to. It would just take a lot of purification at the end and get it to the point where it's edible. But the weird thing is that sodium by itself is poisonous, and if you eat a spoonful of that, you're gonna die. Chlorine by itself, if you inhale enough of that, you will die. But when you put those two things together, they make sodium chloride, which is a compound that has totally different physical and chemical properties from the elements in their separate form, right? You know, sodium chloride is a white solid, and it's a granular solid, all right? So that's just some information about mixtures and pure substances that can be broken down into compounds and elements, right? So we talked about mixtures and how if it's a homogeneous mixture, it's got the same composition. So let me give you that. And then I think we're going to stop there after this. We got about 3 minutes left. All right. So when we talk about, let me just wrap this discussion up about mixtures, right? Mixtures are a combination of two or more types of matter. Right? Again, the difference in a mixture and a pure substance is how you combine and how you take them apart. Pure substances, especially compounds, are chemically derived. Mixtures are physically derived. Right? And they can be physically separated. Zoom in. I'll zoom back out for those of you who are taking notes. So they can be physically mixed together. Same way you mix them together, you can physically separate them. Right. In the case of a mixture that's a solution, that's a little bit more difficult, but you can do a distillation and of a liquid, of a solution that's a liquid, and get the components out. So again, you have homogeneous mixtures, right? And again, a homogeneous mixture has the same composition. Right, and if it's heterogeneous, then the composition is going to vary. Right. Again, another example of something that's heterogeneous would be like Italian dressing. Right. You could take a spoonful of Italian dressing from Kraft and a spoonful from what is it? Newman's Own. And in each spoonful, there's going to be different amounts of garlic, different amounts of olive oil, different amounts of red pepper, so on and so forth. All right. So mixtures can be homogeneous or heterogeneous, and you combine two types of matter physically. All right. And then they can be physically separated. Compounds are chemically combined and they can be chemically separated. All right. So with that being said, we're going to stop here on when we come back on Friday, we're going to start looking at some measurements. And Thursday, we're going to go through, we'll spend some time here discussing mixtures and things like that. We're going to just go through some questions about how to identify mixtures, how to identify compounds and things like that. And then on Friday, we'll start measurements. So that'll get a little bit more exciting. Again, if you don't have a book, there's a link to a free ebook on Blackboard. Please get it. You got to have something to look at outside of class. All right. Any questions?
Is the lab class going to be the same link?
No, I think it's the old link that we were using for this class because I hadn't set up a recurring link yet. Well, I have it, but I didn't email it out.
Okay.
So if you have access to the link that you use for this class on Monday, just use that one.
All right.
And I'll see anybody who's in lab, I'll see you in 8 minutes. I need 8 minutes to catch my breath. All right, any other questions?
Are you the lab teacher for Tuesday?
No, just on Wednesday.
All right.
Yeah, I think on what time Tuesday? The 2 o'clock or the 9 o'clock?
2?
Yeah, I think that's Dr. Gines. Yeah, that's Dr. Gines. Yeah, I'm teaching so many classes, I couldn't add another one. So yeah, but he's good though. You'll like him. He's a good guy and a good teacher. All right. Any other questions?
No, sir.
All right, we're gonna stop here. If you're in lab, again, go to Blackboard and use the link that's in the announcement, and I'll see y'all back at 2 o'clock.